Hello, hello. So I'm bordering on finishing up this CloudAtmosphere plugin. We're looking at the stylized variant. It can also do realistic variants. This would be for like a stylized planet with a much thicker atmosphere so that you can really see the details. But I also have a version that looks more realistic. It can all be done with the same shader. So what I'm gonna do here is we're just gonna kind of go over the features of this and what it does and the changes that I've done the past 2 weeks. So basically I'm in the process of migrating a bunch of projects to Unreal 5.7.3 and merging them together. So right now I have my voxel project migrated. That'll be a whole nother demo. And I have a new CloudAtmosphere plugin project that I'm working on, which I'm gonna basically put out the public repo for that once I finish the blueprint wrapper for all this. But the material function, the shader, and all of that is completely done. I don't think it can really be improved any further, short of maybe like a separate light pass, which is complicated to like find light intersects with actual surfaces and not just a computed planet radius. But those are all very minor. So first off, the major change that I've done is in Unreal 5.7, or it's actually 5.5 and above, they added the ability to render to the user scene texture from a material rather than having to do like complicated setups of render targets. And that basically allows us to do a multi-stage pipeline in our post-process effects. So the primary benefit that gives us is the ability to render this downsampled, so at about half resolution, and then upscale it. So if I had added that, there's a lot of stuff that hoops that I had to go through. I wouldn't recommend it. The user scene texture is not perfect at this point, and it shares a bug with a lot of ray marching stuff that goes through TAA or temporal super resolution. Also shares this bug where basically it's computing your camera vector in the undownsampled space, which throws everything off and will cause, for example, if you have any ray marching effects that you are not doing the modifications that I figured out here, and you're using TAA or temporal super resolution, they will be offset from their center, which this is not. And the reason for that is because it's basically doing downsampling to go into maybe the top left quarter of the screen, and then it's stretching that to fill the entire screen. But it's not updating the camera vector node to match the downsampled area of the screen. So what you end up getting is the top quarter of the screen, but the camera vector's unmodified. So you get like a quarter of whatever the thing you're looking at. And then that gets upsampled to stretch to fill the whole screen, which means that now your object's origin is offset from where you actually see it, because you just upscaled like a quarter of this to fill the entire screen. So now your object center is off, your scale is off, everything is off. So we did figure that out. There is a transformation that we are doing here, and it requires us to feed in the size of the render target that our downsampled images being rendered into. And we don't have that at the time of this processing, so we got around that. And I'll just show this so that anybody that ends up in the same boat can kind of know what's going on. If I look at my post process here and we go to materials, we see that we have a MTUCA preprocess, MTUCA default, and MTUCA postprocess. So default here is our shader instance of our compute shader for the atmosphere data. This is what actually renders the atmosphere. Post process is doing our upscaling and a blur pass on the atmosphere. And pre-process does nothing. What it does do, though, is render at the same downsampling resolution as our actual shader, and it comes before it in the pipeline. So in our actual shader, in order to be able to pull in the precise render target size, we pull in the pre-process user scene texture. We get the render target size from that, and then we use the same downsampling ratio between the two. So it will be the same as the one that this is rendering into. And that's how we ended up doing this. This dramatically speeds up everything. It means we have four times less ray marching samples, so it's 4 times as fast, which means that we can increase things like step counts, light step counts, things that actually contribute to the quality of the number of noise samples. We now, instead of doing 1 noise sample in our loop cloud density, we do 2, which allows us to have more detailed clouds, which we'll be able to see once I go a little bit closer to this effect here. So real quick, just on our default settings, we'll kind of zoom down and we can take a look at some of the stuff I'm talking about. So if you've seen before, you may notice that there's a lot more detail in the cloud. We have noise sliders to control all of this. There's no more slicing or anything like that because we figured out all our noise offsets. There is a little bit of jitter that can happen while you're moving, but all in all, I think it's a pretty safe price to pay. If you go below the surface of the planet, you get artifacting, but like you're not supposed to do that. Everything is computed in 1 ray marching pass, which is why our clouds can shade the atmosphere itself, and the atmosphere can shade the clouds, and our clouds get our Rayleigh scattering colors from where they're at in the atmosphere. Our sunset clouds are more orangish, whereas our daytime clouds are white. Our night sky has ambience, or cloud ambience in the night sky, and things like that. This also means that we get surface shadowing on the ground, and we get God rays, which we will see when I mess with cloud coverage here in a little bit. We have full 3-channel scattering controls for everything. The clouds, the atmosphere, absorption of the atmosphere, absorption of the clouds. We have a bunch of weights that we can use to control the cloud noise. We can control light color, which will change the color of everything because it's our input to our scattering equations. We can control all of our ray marching params, which increase or decrease our performance at the expense of quality. So here I was able to ramp these up quite significantly from like 32 atmosphere steps to 64. I kept 64 cloud steps because I think it was enough. We had 8 atmosphere light steps before, but we went up from 16 to 32 cloud light steps, which increases the like quality of the shadows of our clouds in the atmosphere, like the atmosphere shadowing of the clouds themselves. And then jitter factor, which is used to basically kind of blur everything almost. We do 2 types of jitter. We do a step size jitter. At 0.5, that means our steps will jitter between half step length and 1.5 step length. This gets rid of banding and correlation between different rays, so you won't see like slices in your main march rays. And then the other type of jitter we do is in our light march. Rather than jittering the step sizes for our light march, we jitter our light direction within a cone, which softens shadows and also decorrelates like lighting slices. So with the combination of those 2 types of jitter, we were able to solve like almost all of the slicing issues. You can still see a little bit of noise here, but like I said, that's just kind of the price you're going to pay for the downsampling. I think it's fine. Like in motion, it's almost imperceptible. And as I'll show soon, your clouds are almost always going to be animated, which will also decrease it. So yeah, and then let's just start going over the parameters here. So first we have our atmosphere scattering parameters. Again, I have a preset here set to our stylized atmosphere, which has a thicker shell, fluffier, taller clouds. A real atmosphere would be much thinner than this, and we can do that as well, but it would require changes here, and maybe I'll go over that one tomorrow or something like that. Okay, so the various effects here. Rayleigh beta. This is our Rayleigh scattering for the atmosphere. If we change this, it changes the scattering coefficients of our atmosphere. Like if we go to red, then we have a red atmosphere with bluer sunsets. If we go to blue, we have a bluer atmosphere with oranger sunsets, kind of like real life. If we can go to all kinds of alien colors, and we automatically get all the scattering updated in all the different pieces. So like your clouds don't have separate scattering, like they're going to catch the Rayleigh from your changed Rayleigh scattering, etc, etc. But generally speaking, we go with like a blue. I'll go ahead and cancel that. Rayleigh height. This controls the height of the maximum Rayleigh scattering. So right now we're at 0.1, and this is all proportional to the atmosphere scale. So this is what gets you like the shell, like more of like a shell if you push this higher relative to the atmosphere. If you push it lower, you get more of like a fuzzy atmosphere. So for stylized, we have it pretty low. For the accurate version of this, we have it pretty high. Mie beta, this is our sunlight scattering. So if I go in the sky, that would be this glow here. We can control all three channels here. We can control intensity. And basically we just have it very close to a white, but with a little bit of a tint towards yellow. You can control this, and it would change your sunset glow and your sun halo glow. But most of the time, this would be fine, and you would just let that stuff get controlled by light color. Mie height is the same thing as Rayleigh height. It controls the height of the maximum effect of the Rayleigh. Usually we want it under our Mie height, but above the minimum radius. Mie G, this is going to control the amount of scattering here. With a 0.9, you can see it's about that big. If I bring it up to 0.95, it will concentrate the scattering more around where the light source is. I feel like a 0.9 is pretty good. That gets you a good glow for your sunsets, where you get this kind of horizon glow for the sunset. Atmosphere absorption beta, absorption height, and fall off. I would suggest not messing with these too much unless you just want to experiment, but basically this controls the rate that light is attenuated out of the atmosphere. This is set pretty effectively here. You would want it to kind of line up with where like the ozone layer would be. So I mean, you could put it at 0.1. It's going to be really hard to perceive a distance because the atmosphere doesn't absorb much unless you're trying to do some specific effect. Like maybe we want to be on Venus and we want a huge amount of atmospheric absorption, like to basically have us in the dark if we're deep into it at all. Then you could tweak this and make the atmosphere much more absorptive of light so that it gets darker as you get down close to the bottom. But generally speaking, you won't mess with this that much because like open air is not absorbing that much light. And then finally, atmosphere ambient. There's a bug with moving around in the editor where the bloom or the exposure ramps up instantly as soon as you move the camera. So if I look this way and then look this way, it fades in slowly. But if I move around and look around, it's instant. So don't worry about that. But the atmosphere ambient is the basically scattered light of the atmosphere when it's completely in shadow. So here we have like a 0.117. We could probably even go lower than this. Let's try like a 0.1. It will darken your night sky, but you still get this like nice little kind of horizon gradient. All right, great. So that covers the atmosphere scattering params. We'll go to the cloud scattering params. This is very similar, except it's controlling the scattering through the clouds. So if we take a look at, let's say this cloud here, because we got a little bit of Raleigh mixed in there, we got our cloud scattering. So if I was to change this to like 300, our clouds scatter more light, so they become apparently denser. 1500, even denser than that. Usually around 100, 150 is where I set this. But one cool thing that I wanted was the ability to represent like exotic or imaginary materials, right? So right now, we're just scattering white, pretty much. And that's what most clouds scatter. But we can change the cloud scattering coefficients to scatter different rates of colors as well, and that will change the overall color of the bright side of the cloud. Likewise, we have a cloud absorption amount. Here I have it set to 25. This changes how fast the light is absorbed going through the cloud, which affects both cloud darkness and the shadows the clouds cast through the atmosphere itself. So, for example, if we go up to 100, we get more cloud absorption, so the light is getting eaten more quickly as it passes through the cloud. We're getting more intense shadows on the atmosphere. We're getting darker areas of dense clouds even when we're in the light. And one kind of neat thing about this, I haven't figured out a use for it yet exactly, but you'll notice that this is also a vector. So we don't just have one absorption coefficient. We can control the individual absorption rates of the different wavelengths of light. So say I absorbed a lot of, or say I absorbed a lot more blue and green than red, then the light making it through the cloud at that point is more red. Our shaded portions of the cloud become more red, and the light that we experience when we're in shadow from the cloud is also more red. 1,000 obviously being a ridiculous value to set on this. Even 100 is probably too high. But yeah, so this is really neat, I think. I don't, like, again, it's not really how it works in real life most of the time, but if I scatter more blue, we get yellow light. If I scatter more green, we get purple light, etc., etc. And we'll just kind of reset this back to default. Cloud ambient. Okay, that's simple. It's just the ambient cloud color of our clouds that are in shadow. So that's like your minimum cloud color. And again, this is probably too high. We'll probably take it down to like 0.5 or something like that. Now this would be what color your clouds are on the dark side of the planet, and also when they're fully shadowed. One cool thing that I've managed to do with this shader is true opacity, so that even on the dark side of the planet, the clouds will obscure the sky, obscure the ground. It didn't used to do that because I was working in a like purely additive fashion, so like lights would shine through and things like that. That doesn't happen anymore. Now the clouds are fully opaque when they're fully dense, and it works just fine. Finally, we have this cloud phase param, so we use a dual lobe. Puppies, would you stop fucking around? We use a dual lobe phase function for our clouds, and that has 3 inputs, and then we also have a multi-scattering approximation. Stop. Jake, stop. We also have a multi-scattering approximation that is in the alpha value of this. If we mouse over it, it will say as much. I have descriptions in the material for all of these. Minimum ambient color. Oh wait, no, wrong one. Cloud phase params. My dogs are trying to fight each other, and I'm trying to stop them. So yeah, R is forward scatter, G is back scatter, B is forward back blend, and A is multi-scatter intensity. So all 4 channels of this are used, and it controls our phase function for the clouds. I wouldn't mess with this too much from what the default is. I'm not going to really go into it, but like if you wanted to play with it, you could. Stop. Stop. Hey, no. Chill. Chill the heck out. You're being a little annoying turd, and you need to stop. Okay. Wait, why is this? Okay, I didn't add these in. This should be in the cloud noise parameter, so that's something I have to fix. Basically, this is our. I'll go ahead and go into. We'll go into this in a moment. Light. Again, we can change the light color, and that changes everything because it's the input into all these equations. And then light direction we control as well. This controls the direction the light's coming from. It's only working in positive values here, but you can set negative values to it programmatically to represent any direction. Very simple light controls. Ray March. Did I talk about these? Yeah, these are our step values, all the stuff that controls our performance and quality of the Ray March itself. Once you find a good sweet spot for these, you probably won't touch them ever again. Scale and position. Okay, this is what defines the actual shape of our atmosphere. So we have planet center and radius here. Planet center is a vector. It takes the center that you want this to appear on in your scene. Planet radius is how big in units you want this effect to be. Right now we have it set to, looks like, what, 9 million? Stop. 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 Okay, sorry. These puppies decided to start freaking out as soon as I started doing this. So what are we at? 1, 2, 3, 4, 5, 6. Yeah, 9 million. So 1, 2, 3, 4, 5. So this would be a 90-kilometer atmosphere. You would go much bigger than this, obviously. You would go much bigger than this, obviously, to do a full planet, but we can go bigger. I just have it set to this for demo purposes. Atmosphere height scale. So one big change that I made to this shader from my last implementation is I wanted the only discrete values we had to set that were based on real world data and not proportions to be the planet radius and the planet center. So that's all you need to know baseline to position your atmosphere. To do that, we move to coefficients for all of our height scales for everything else. So atmosphere height scale is saying, I want my atmosphere to be half as thick as my planet radius at what I have it set here, 0.5. So with a 0.5 height scale, your atmosphere bounds are half the size of your planet radius. Then likewise, cloud outer and inner height scales are the positions within your atmosphere height scale where your cloud upper and lower bands terminate. So it's basically the shell in which your clouds can render. And then finally, atmosphere floor offset. What you will find is if you have a planet of 9 million units and you have your radius set to 9 million units, and again, you would want it set to whatever the minimum elevation possible from your planet after the terrain's been generated. So if you have rivers and valleys and stuff, your planet radius should be the minimum height of any of that stuff, as low as the player could go. So what the atmosphere floor offset does is if you set this dead on, because you probably don't want to have to think oh, my planet is 9 million units, but I don't want my atmosphere to be dead on at the exact boundary of my planet scale, so I need to make it a little bit smaller. Well, you don't have to do that here. The atmosphere floor offset will push the atmosphere down a little bit. We'll push the atmosphere down a little bit, just a touch. So usually you would put a 0.001, and it will just nudge the atmosphere down so that you don't have to worry about computing a different planet radius than whatever the object that you're trying to attach this to is. Okay, great. So let's see what's next. No, stop. Why did you decide to start being a spaz? Okay. So next we'll go to the, let's see, so we've gone over this. So I think the only thing left we have to go over is the cloud noise parameters, which I haven't moved these in there, but these would be in the cloud noise parameters. So we have a cloud volume texture. You can use, I use this Perlin Worley balance. It's a part of the engine. It's basically 4 levels of noise. So it's like a FBM 4, FBM depth 4. So like you have a large scale noise, then in the next channel you have a medium scale noise, a small scale noise, and a smaller scale noise baked into one volume texture. So you could use other textures if you want to, but you would want to bake them the same way, because otherwise you're going to lose like that FBM effect. Because with 2 samples of this, we're basically getting FBM level 8, right? Because we have 1 sample at large scale to block out the shapes and major features of the clouds, and then we have another sample at smaller scales to block out the minor details and like the little minor variation at small scales of the cloud. So whatever you put in here, you would want to have that same format, whatever volume texture you put in here. I think this is 256 by 256, or maybe 128, I'm not sure, but either way, you would want that. I'm gonna have to go deal with these dogs. Hang on, we'll finish this, I promise. Hey, you guys, chill the fuck out. Come. 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 Okay. They relaxed. Animation weights we'll look at last. Cloud coverage. Very simple. How much clouds are there in the scene? If we decrease cloud coverage, we get less clouds. If we increase it, we get more clouds. This is where I was talking about it would be very apparent, like the God rays. If we take like a really heavy cloud coverage and we go down to the surface, you can see that we're getting like heavy God rays. And that's because the light's getting absorbed actually by the clouds. So we just naturally get the God rays propagating through the rest of the atmosphere. So yeah, we'll go back to 0.5, which is my default. Or maybe like a 0.6. Cloud density multiplier. So cloud coverage controls the clouds that are already there. Cloud density multiplier controls the density of the clouds after they're already thresholded. So like increasing this won't increase your cloud coverage, but it will increase the overall thickness of the clouds and the way they behave. Cloud noise frequency. This controls the base scale of the clouds. So if I increase this, our clouds get bigger. If I decrease this, our clouds get smaller. Pretty simple. Cloud noise invert. So we have 4 channels of noise. For both the detail and the overall layer, we compute the 1 minus of our noise sample in addition to our noise sample, and that allows us to do things like flip which channels or flip which values being used for R. And this will change the actual layout and the effect of the noise itself and what it ends up looking like. Yeah, so that's what that does. You're basically blending. It gives you a little bit more variance control, but it becomes very apparent if we look at the detail noise invert, which you have set to 1 here. But if I was to say flip this to 0, it changes the way our fine noise is applied to be less poofy and more subtracty. So like here you can see it looks like we have our clouds are a little bit more wispy and less like fluffy. So that's like the example of why you would use this. All right, what else we got? Cloud noise invert, cloud noise weights. This controls the weight of the individual layers of noise. So remember, for each of these we have 4 layers. So this value here is controlling the weights that each layer is applied at, and it will change the patterns of noise you got. So you would just like you would want to be able to like mess around with this to figure out, you know, what's a good parameter, what do you like the looks of. Detail or road strength increases the rate at which our fine noise eats away at the larger clouds. Detail noise frequency increases the basically the scale of the smaller noise, the finer noise. Detailed noise invert we already talked about, and detailed noise weights is just like the other one. This is controlling the weights of the individual components of the sample. Okay, and finally, cloud height curve max and min. This changes the shaping of the top and bottoms of the clouds. So like, for instance, if I bring this down, our cloud top is fading out sooner. If we had this at 1, we would just have a hard line cut off. We don't want that. So at like I have the default set at 0.7, 0.3. This controls the bottom of the clouds, same way. If you don't have a big enough value here, you're gonna get these hard cutoff lines. But like a 0.1 at least, a 0.3, I think 0.7, 0.3 is usually like a pretty good sweet spot. And these are gonna move into cloud noise parameters. And finally, we have animation vectors. So this just changes the amount of animation we get in each axis. So red is X, green is Y, blue is Z. So if we wanted our clouds to go up and down on the planet, we could do this, and now our clouds are moving down. We could also do -1. No, we have to expand it to do that. Hang on. We could also do -1. Now they're moving up. -10. Now they're moving up very quickly. This is not realistic. But you get the idea. So for like X, we want them flying around on the X-axis. We could do this. Now they just go really, really fast. So yeah, and of course this you can see from the ground as well. And all the lighting and everything will update as it happens. Our shadows are updating. The clouds are passing over our head. So yeah, that's pretty much it. That's the breakdown of the whole thing. And I would stick around and talk a little bit more about this, but these dogs are being a huge pain in my butt right now, so I'm actually going to end it here, and I will talk about this a little bit more once I finish the blueprint wrapper for all of this. But that's all the functions, or that's all the parameters, and I'm really happy with this. It runs quickly. I like the look of it. It looks good from outside the atmosphere. It looks good from inside the atmosphere. There's no crazy transition logic that occurs in order for us to be able to transition between those two. The graininess is not super grainy unless you're in those like high transition zones, but you know, it is what it is. We have full opacity on the clouds. We have accurate scattering. We have accurate coloring. We have really fine-grained detail control over everything, and it sets us up really well to be able to do like a proceduralization harness to just generate a bunch of different random atmospheres. So yeah, that's it for now. Later.